Hey guys, welcome back to another video. So, as you can see here, I have a list of a bunch of random stuff, and what I want to do is order them, and I want to order them from highest to lowest boiling point or melting point or whatever. It's the same trend. Order them from highest to lowest melting point. Uh, let me. I'm trying to use a bit of shorthand because um, MS Paint writing is really not fun. So high to low boiling point. Pause the video now if you want to try and come back for the solution in a couple minutes and a couple seconds even. Alright, now that you're back, presumably, I'm going to first erase this so I can get some more space here. The first thing I like to do is first, generally I like to, since I have a random assortment of compounds, I know the general trend anyway is I first want to sort of go general and work down specifically. So I know that network covalent is greater than metal, which is greater than ionic, which is greater than uh, molecular struct. So molecular. So first I want to order my stuff sort of like that. I want to categorize everything into. I first want to fit everything into each category, and then I can sort of get a sense to where I want to put stuff. Um, so I know graphite is network covalent, so that goes there. I know this is just a pure metal, so that goes there. Magnesium sulfate, that's an ionic compound, that can go there. And then all these can go in this bin. So, alright, this is good. So already we've organized half this list. So graphite, aluminum, and so there you go. That's already half the battle done just by doing that sort of step. Now, I want to break this down. I want to break this down. Yeah, I want to break these down here into ordering them. So now I just have to consider the molecular bit. Now, firstly, what I want to consider is type of intermolecular force. So, okay, so here, so first, draw out Lewis structures if you need to. So C O O H, and then C O H H H H. I know that that's positive, and I know that, okay, so this would be positive going to negative, that, 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 but those all cancel. Here we get a positive charge, here we get a negative charge accumulating. So therefore, that's polar, and even more so, since I'm smart enough to notice that, look, there's an O directly attached to an H. Therefore, I can say that this will probably do H bonding. Whoops, I did a really bad job spelling that. So H. So that has H bonds, right? And I know that for molecular substances, I can break this down even further. Where do I want to break this down to? Here. I need some more space. Here. What I can do is I can further break this down into H bonds have higher melting points than dipole forces, which have greater strength than LDF. So I can split this molecular thing up into H bonds, dipole, and London dispersion forces. And then, so C, So I'm first just drawing all these Lewis structures here, just so I get an idea as to what um, everything is sort of doing. And I think this is a really good idea, even on a multiple choice exam, just so that you know what, just so you don't make careless mistakes for one, and so that you get a sort of full context as to what's happening. And then I want to determine polarity. That goes up and up. That goes up and up. And since there's no electronegativity difference here, there's no polarity associated with that. So the only one here that would interact with, since they're nonpolar, is LDF. And then similarly here, all the dipole moments cancel. Here, 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 here. This is all nonpolar bonds, so LDF. And then lastly, with this carboxylic acid, I can again go, okay, positive to negative, no, positive to negative, positive to negative, positive to negative, and positive to negative. So clearly here, there is a centralization of negative charge here and here. And again, since I'm smart enough, since I'm paying attention here, there's this OH group here, and since this H is directly attached to an O, this one is capable of hydrogen bonding, so H bond. Alright, so that's clearly helped us in some way, because we can say that these two would be higher up than these two, right? Now, let me erase some of these dipole. Let me erase some of these arrows here, just so we can have some clarity here. Let me just... So now that we've determined what each would go through, I'm going to erase my dipole arrows, just to make everything a little bit neater. In fact, what I can do is I can just, rather than keep everything, I'm just going to erase it. But before I do that, I'm going to make a mental note here that H bond, LDF, and LDF. Right? So I'm just going to make a note there to myself, and I'm going to erase everything. So, alright. Now, the next thing I want to do is I want to focus specifically on the hydrogen bonding ones, since those will probably come higher up, right? So I want to focus on our hydrogen bonding buddies. So COH, H. And I want to draw maybe 2 molecules just so I can play around with intermolecular forces. Since these things interact often in groups, you don't have to draw a bunch of molecules. However, I do recommend drawing a pair of them. And then similarly with our carboxylic acid, OH, H, C, double bonded OH. And what I can notice here is that since this will partake in hydrogen bonding, we can attach this particular hydrogen either to this lone pair or this lone pair, and it would still be a hydrogen bond. And similarly, I can do it here or here. But with this particular molecule, but with the carboxylic acid, here, let me move this a little bit so it's maybe a little bit clearer to manipulate. Let's move that around a little bit such that it's easier for me to show you what I want to show you. This hydrogen here, however, this hydrogen can partake in hydrogen bonding, so it can go here or here, like we showed, or it can go here or here. And similarly, we can have a similar effect with the possibilities or we can go here, right? So there's two options for this hydrogen here, right, for where it can hydrogen bond. But here we can clearly see that there's four options where it can place its hydrogen bond. And because 4 is greater than 2, this one will pack more. And since there's more packing involved, the acid, can I find my mouse? Yeah, the acid here will have a higher boiling point than the alcohol. So therefore, since there's more packing, the alcohol has a lower boiling point. The carboxylic acid has a higher boiling point than the alcohol. So right there, we can now put H. Oh, whoops! I need to switch back to my black pen. Yeah, HCOOH CH3OH. Right? And then lastly, we now have to consider these two. And the way you would do that is you can compare molecular mass, because molecular mass, if there's more atoms there, right, there's just more electrons, and more electrons means that there's more electrons flying around, means that if they all move around more, you can polarize it more easily. Since there's more electrons, you can have greater partial charges. And what we can denote here is that clearly the greater the charge, the electric charge on the things that are being attracted to each other, the greater the electric charge on the items, the stronger the forces of attraction between them. So therefore, since this is C2H4 and C2H6, this one is a higher molecular mass, albeit only slightly higher, but still nonetheless it is higher, so it would go C2H6, and then I'm running out of space here, C2H4. And that's our answer. Thank you very much for watching. Don't forget to like and subscribe, all that fun stuff.